limit theorem for proportions. So what that basically says is that if you take a sample from a large enough population and you continually take samples, then you get a thing that's called the sampling distribution. So suppose I have some population, and let's just say I know some fact. So that seems a bit unusual, but let's assume we do it. Suppose that we know that 20% of Americans smoke. Let's say we've studied it long enough to know that right now 20% of Americans smoke. So if you took lots of samples, and you notice that you turn percentages into decimals for this, that's just one of the quirks, you get 20%. So the mean of the sampling distribution, I guess I'll put it here, is equal to the population proportion, 20%. Now suppose you take a sample and there's 100 people in your sample. Then the standard deviation of this, which is also called the standard error. So I want you to just think of standard error as standard deviation. It's given the special name standard error in this context because we're talking about a sampling distribution. So it's just a name. And it's got a really ugly formula. It's the square root of 1 minus p over n. So if you wanted to know what is the standard deviation of samples of size 100, it would be this number here. So in my particular question, it would be 0.2. 1 minus p is 1, take away that number, so it's 0.8. And the whole thing is over 100. And I'll do a quick calculation on that and see what we get. So we get the square root of 0.2 times 0.8 divided by, in this case, 100. And we're looking at, normally you get a really ugly decimal, but I get lucky here. You got that. So if you took lots and lots of sample size 100, you would get a distribution like this. It's called the sampling distribution. The mean would be the exact same value as the population, and it would have a standard error of 0.4. So you can imagine 0.24, 0.28, 0.32, 0.16, 0.12, 0.8. And that's what the central limit theorem says. It says if you take a sample from a population of a given size, in this case 100, then the mean of the sampling distribution, that's all the samples you could get, would look like this. So you imagine you did thousands upon thousands of little samples of 100 people. Sometimes you'd get an answer as big as 32% said they smoke, and sometimes you get an answer maybe of 16% they smoked, but most of your samples would probably agree with the population, which is 20%. Now you think about it, there's a lot of logic in that. If 20% of Americans smoke and you just pick randomly 100, you don't expect 20% of them, exactly 20% of them to smoke, right? Don't you get a bit of variation? You know, sometimes your sample, you get more smokers. Sometimes you pick a sample, you get a little bit less. So what the sampling distribution is, it puts a structure on that to show you what kind of variation you would get from a sample size of 100. Okay, so that's just the background theory to it. So it's called the central limit theorem, CLT for short. Now, for this theory to work, or theorem to work, you need 3 conditions to be true. And after we've done this little intro, I'm going to show you some homework questions to show you how this works. Now, the three conditions are, the first one, when you get your sample needs to be random and independent. So if I'm going to pick 100 Americans and find out whether they smoke or not, that 100, that sample of 100 needs to be random, right? I just randomly pick some people, right? I didn't, for instance, just find every single Robertson that I know, family members and whatever, and find out if they smoked. Because you know that smoking is a family trait. If your mum and dad and all your uncles and aunts don't smoke, do you know the chances of their children smoking is very low? But if everybody in your family, including your uncles and aunts, are all heavy smokers, you realise that there's a very good chance that your children are going to be smokers as well, right? So that wouldn't be independent or random, right? Second condition is that the sample that you take has to be big. And that's a very vague word. We'll come into what is big. But can you imagine it wouldn't be a good idea for me to pick a sample of 2 people? Because the answers I'm going to get are 100% are smokers, nobody smokes, or 50% smoke. You know, too small. So how do you test for big? Well, you take your sample size and you multiply it by the P, and it has to be bigger than 10. And you take the sample and you multiply it by 1 minus P, and it has to be bigger than 10. So let's see if that would work for my sample. I got 100, right, in my sample. And the P value for Americans who smoke is 20%. So 100 times 0.2 is 20. That means 100 is a big enough sample, right? If I only picked 10 people as my sample, 10 times 0.2, 20% of 10 would be 2 people, too small. You see how it works? N times P. Now you do the other one, N times 1 minus P. Well, P is 20%, so 1 minus P is the 80%, and it works for that. And the last is a little bit bigger. You need a big population. This one's probably the easiest one. There is a rule for what a big population is, and the rule is your sample can't be more than 10% of the population. But normally we just say, you know, it's pretty obvious that there's a lot of Americans in the world. It's a big population, right? So we just kind of go with the flow with that one. Well, if you know these things are true, then the central limit theorem that we've got up here is valid, and you can use it to calculate questions. So I'm going to jump, hopefully, to a PDF. And see if it's this one. No, that's 7.4. Okay, there we are. Are you looking at 7.3? Does it say at the top here, homework math 146, section 7.3?
No, it says 7.4.
Okay, so I'm going to go back out and back in and hopefully get 7.3. Oh, that is interesting. Oh, okay. Then I know what I'm going to have to do. I'm going to have to close 7.4 so you can see 7.3. Zoom can be pernickety. Darn it, where is it? There, are you now looking at 7.3?
Yes.
Yeah, okay. So 7.3 starts off with a couple of questions that basically just ask you, they give you a story, and they ask you if the conditions for the central limit theorem work. Now, to remind you, the conditions are, the first one is it random and independent? The second one, is there a large sample size? And the third one, is the population reasonably big? Right. So in this story, according to an article, 74% of high school seniors have a driving license. Suppose we take a random sample of 300 of these and find the proportion who have a driver's license. Find the probability that 78% of the sample have a driver license. First thing we're going to do is verify the central limit theorem. Well, if you pick a sample of 3,000 random high school students, is the sample going to be random and independent? Yep, you've kind of told me when you use the words random sample here, right? So I would say it holds, assuming independence. I don't think there's any reason to suggest that they picked 300 people that were related or somehow connected. Now, the large sample, the quick test for that is 74% of 300. Is that bigger than 10? And the answer is yes, it's a lot bigger. So the large sample condition is met, so it holds. Is it a big population? I think there's enough seniors in America to be a big enough sample population, right? So it holds. So can reasonably assumed. So you just fill in the words that say, yes, it's random. Yes, the sample's big enough. Yes, the population is big enough. And I better get a well done here. Does it say nice work? It says nice work for me. Okay, cool. Now it comes on to the next piece of the puzzle. What's the probability that more than 78% of your sample has a driving license? Okay, so I'm going to write down some of the information, then we'll return back to my screen. So right now we know that the population of high schools is 74%, and we know that the sample size is 300, and that we're being asked to find what's the probability that our sample, we'll call it X, is more than 78%. Okay, and they want everything to decimal places, so we'll figure that out in a second. Let's stop sharing. Right. Are you all seeing the big screen with the writing? Okay.
Yes.
So we got the simple, the central limit theorem sorted out. Let's look at the numbers that we need. We've got 0.74. We've got 300. Let's get the standard error. Right, which is basically just the standard deviation. It's just its name. For a population sample, we call it that. And it's P, 1 minus P over N. Everything is in decimals. Even that's eventually going to be a decimal. So P is 0.74. 1 minus P is 1 take away this decimal, which is 0.26. And the whole thing is going to be divided by 300. Now I'm just going to do this in my calculator. Hopefully I won't screw up. So 0.74 times 0.26, all divided by 300. And I get the answer 0.0253 to 3 decimal places. Are we all comfortable about how I calculated the standard error, where that number here came from?
Yes, sir.
We're good? Now, I'm going to do this visually because I'm a visual person. If I did the central limit theorem sample distribution, if I drew the picture of what all the samples look like, right in the middle would be 74, that's the mean. So this guy up here is the mean. This guy here is essentially the standard deviation. So can you imagine what that guy would look like, right? Now we're being asked to find the probability that we have a sample bigger than 0.78. So if you can imagine that 0.78 was, say, about here, that's the bit they want us to find, right? Bigger than 0.78. And here's the good news. We know how to do that because this is a normal distribution. And we're trying to find what's the probability that the thing is bigger than 0.78. So what I'm now going to do is I'm going to use my calculator to figure out what the answer is. So to get a guy that's greater than 0.78, you go setting distribution, you choose option 2, which we should have been doing for quite a lot of other questions. Now, if you want bigger than 0.78, that means 0.78 and everything bigger. What number do I have to put in the upper?
9999.
Yeah, as many 9s as you feel like. You can put in 5 if you want, right? That's how you do 0.78 or bigger. Okay. Now, suppose it was 0.78 or less, right? A different question. But suppose it was less than 0.78. Wouldn't this number that says lower, wouldn't this be negative 9999? And wouldn't the upper one be 0.78? So,
Yes.
you know, it's either one or the other, depending on the story. Now, the guy that they're calling the mean is the population number, which is 0.74. And the guy they're calling sigma, the standard deviation, we call it standard error, but it's the same thing. And it's 0.0253, right? We already had that. So I'm just going to write down what that looks like. It's a normal CDF, and it's 0.78, 999, a 74, and a 0.0253. Okay, so when I hit enter, I should be done. And the answer that we get is 0.057 to 3 decimal places. We comfortable about how we found the probability that you get bigger than 0.78? 0.78 or bigger. The population mean is 0.74. The population standard deviation, although you can't see it, be over here, is the 0.0253. So let's return back to what it looks like. And it looks like that guy. So I should, fingers crossed, be able to answer that question. And it says type it is an integer or decimal rounded to 3 decimal places. So I'm hoping it's got 0.057 and I didn't screw up somewhere. And excellent, I got it right. That is a classic central limit theorem question. That's the kind of look that they have to them, right? Where you're given some population percentage, like 74% in this case. You're given a sample size, in this case it's 300, and you want to know what's the probability that I have a sample who's bigger than this percentage or less than that percentage. Are we okay with that?
Yes, sir.
Okay, so if I just keep this screen for a minute, and I have no idea whether I have to go it around, but let's find out. Can you see question number 2 now, or do I need to go out in it?
Yes.
It says 2, okay. Now, can you see in this case, the population is going to be 39%, the sample size is going to be 700, and find the probability that you get at most 36%. You see, that's a very similar question to the one that came before. Okay. Oops. So let me make up my own question, and just that way we don't need to do so many ins and outs. So let's suppose that we know, because I guess the government keeps figures like this, that we know the number of people in America who have been to Europe is 34%. Right, so you're given that. Suppose I pick a sample of 400 Americans. What's the probability that this particular sample will have more than 40% of them have been to Europe? So we're going to find the probability that a sample of 400, more than 40% of them have been to Europe, when the typical American number is 34%. So far, so good. So there may be a start to this question that says, prove that the central limit theorem works. And so you'll say, yes, it's random. The sample is big enough. Can you trust me that if you do NP, you get a number bigger than 10? It's pretty easy to do NP, right? Oh, by the way, they tend to give you the number here as a percentage, but you always use a decimal in these questions. So random, yep. Sample big enough, yep. Population America, definitely big enough. We are good to go. So the mean is just going to be 0.34. The standard deviation, which they call standard error, is going to be this fella. In this case, that is going to be 0.34, 0.66, all over 400. Then I just go to my calculator and do what we need to do here. Square root of 0.34 times...
Where'd you get the 66 from?
Oh, 1 subtract 0.34.
Okay.
So you got that guy times 0.66 divided by 400, and I'm looking at 0.024 to 3 decimal places. So that's a preamble. That's the kind of things you need before you can answer the question. So in this one, we're being asked, what's the probability that your sample has more than 40% of people been to Europe? Well, that's going to end up being a normal CDF. 40% or bigger, with a mean of 0.34 and a standard deviation of 0.24. Then I'll just go to our calculator. We'll see if we can make that happen. So second distribution, choice number 2, enter. In this case, it's going to be, and I made a mistake. Do you know what mistake I made? Let me go back and show you. This fella here, right? Oh, I take it back. I thought I wrote the wrong number. I didn't make a mistake at all. In fact, my mistake was thinking I made a mistake. So it's 0.4 or bigger, a mean of 0.34, and a standard deviation called the standard error of 0.024. And then we get 0.006.
I have a question, sir.
Yes.
So if I'm going to use the StatCrunch, the one that it's available on the MyLab, on the
Yes,
assignment itself, is it the same answer? Can I get the same answer?
you will get the same answer, but then you'll have to learn how to do stat crunch. You can
Yeah.
also do this. Some of you might know how to do this on Excel. Um, to keep my life simple and to keep your life simple, I just use the TI-84.
Okay.
But if you want to, it will be the same answer. Yes,
Mm-hmm.
that's
Yeah,
the bottom line.
cause when I tried to do the, like, for example, the question is at most, like,
Ah, okay.
what is the probability that at most 40%? So I tried to do it on the calculator, and I don't know, I always messed up.
Well, I think what
It's easy
maybe
for me for the StatCrunch to use.
well, you use whatever is easiest for you.
Okay.
Right, probability at most 40%. Now, it might simply just be this little mistake. Do you know that that means X is less than or equal to 40%?
Yeah.
So when you do your normal CDF, you'll be looking for 40 or less. So that's negative 999, comma 0.4. And just basically leave the other two numbers as you should alone. Because those two are fixed. And you'll get the right
Okay.
answer.
Okay.
So it might simply be you didn't do this bit right.
Maybe. Yeah.
Right. So be careful with the English language. You know, if you say at most something, you're actually meaning less than that number.
Meaningless. Okay.
Right? So the word most kind of makes you think big, doesn't it? Mostly big. When actually at most means small, less than.
Mm-hmm.
So that's the change, because there are only two directions. Are you bigger than this, or was your sample less than this? Bigger's less likely to cause problems because the way they phrase it is pretty obvious that it's bigger than something, right? But
Okay.
when it's less than, they can say less than 40%, at most 40%. I can't think of another one,
At
but I'm
least.
sure
At
at least,
least.
right? At least
Yeah.
40%. And you know the different types of ways that they can ask these questions. Actually, this one should be at least 40%. No, it shouldn't.
No.
This one is at most. See, I'm talking myself out of it. Right.
Yeah. So at
Yeah,
least is the same as more than, because at
correct.
least. Yeah. Okay.
Yeah. So the English language can throw you that way as well. At least 20% would mean 20% or bigger.
Okay. So
At
it's the
most
same.
20% would mean 20% or less than that.
Less. Okay. Got it.
Are we good with that?
Yes, sir.
Right. Now
Thank
I want to
you.
do right. I want to do one more of these guys just to show you, because the whole section 7.3 is pretty much about finding various versions of this, right? So I'm going to go back in and look at some other examples from the homework. And I'm going to see if I can just jump to, can I jump in this mode? I can. To question 9, right? Have you noticed that question 9 looks almost identical to every other one we've done, right? Because it should. Basically, if you know how to do the ones that we've just done, you know how to do all of them, because they're just going to change the numbers, not the process, right? So let's see what's happening here. In 2018, it was estimated that 41% of the American population watched a specific football game yearly. Okay, so they've just told me that the population is 0.41. Now, they have a sample of 140 Americans, so I'm just writing down n equals 140 then. And they're going to then go in and do all the usual rules connected to that question. So let's say random and independent. I'm pretty sure that they've randomly selected them. So since they said that, I'll say holds, assuming that they're independent. Is the sample large enough? Well, 140 might not seem too big, but 41% of 140 is definitely bigger than 10, so it holds. And is the population, I'm sure that the American population is big enough, so we're done. So we just get through that little hurdle so that we can move on. Now, what they want here is find the probability that the majority, that's more than 50%, watched the game. So we're being asked to find X greater than or equal to 50%. Okay. So that is just the basics of that question, right? The numbers that you need. Now, who's missing? Who do I still need to calculate before I can actually find this fella?
The SE.
Right. Now, it's got that ugly number, or formula, I should say, that looks like that, right?
Yeah.
Okay. Now, in this case, we're talking 0.41 and 0.59 all over 140. So I'm going to do the square root of 0.41. Does that someone tell me the answer there?
Yeah, it's 0.042.
Okay, and okay, I didn't get that. Let me check. So I got 0.068.
Oh.
But I'm not saying I'm right yet, so let me check it again. It's the square root of 0.41 times 0.59 divided by 140, and I get 0.041. Actually, 42 if you round it off.
Yeah.
We agree on that now? Those
Yes.
who did it? Right. So you got all the information here. What you're looking for is greater than 0.5. So we're going to take a normal CDF. If you want to be greater than, it's 0.5 or bigger, with a mean of 0.41 and a standard deviation of that guy. And this then involves me nipping over to the calculator. Let's see what that looks like. It's number 2. And the mean is, the number we're looking at is 0.5 or bigger. And this fella here, the population number is 0.41. And the standard error is 0.042. And the answer is 0.016. So if I kick in one more share and I jump to here, if I type in 0.016, are we good or are we good? You see?
Yes.
So when you're looking at these questions, there are only 2 guys that you're ever really going to deal with. You're going to be dealing with what's the chances that the sample is bigger than 50%, 42%, whatever they give you, or less than that, right? And they might phrase it with at most this number, at least that number, no more than this number, no less than that number, and any other phraseology that eventually boils down to one of these 2 versions. Are we good?
Yes, sir.
Right. So there is a couple of questions right at the end of this group, which oh no, can I get to it quickly? No, okay, then I'm going to do it the hard way. Panicking here. Right, in we go again. I think it's the last two questions I want to talk about, and that's this thing finished. So let's look at 11. In question 11, they give you a very similar story. What makes the last two questions different is that you don't get to use the central limit theorem. So let's show you why. You've got a random sample of 300 people, and the probability is 0.1%. Now, 0.1% of 300 people is 3 people. Actually, it's 0.3 people. It's not big enough. So it fails because the sample is too small. Now, because it fails, okay, I'm trying to move this. There we go. Check answer. That's the end of the question. If the central limit theorem is not allowed, then don't pick A and figure out the percentage, or pick E and figure out the percentage. Because you may go through the process, right? You can plug in numbers into a calculator and it'll tell you an answer, but the answer is not valid. So in the last two questions, you're going to find out that it doesn't work because the sample size is just too small. You know, asking 30 people is not a good idea, or asking 300 when the percentage is so small is also not a good idea. Right? If you had a very, very rare disease, like only 1 in a million Americans have it, you can't pick a sample size of 1,000, because even that would be too small. Because in a sample size of 1,000, isn't it probably likely that you won't even get anybody with that very rare disease? Right? So you won't really get any useful information out of it. So NP, the sample size is N, times the population percentage. Those two must be bigger than 10. If they're not, sample size is too small, end of story. Right, with any questions about that particular group of questions? Are we good?
Sir,
Yes.
so regarding you said the NP must be bigger than 10. So
Correct.
based on that sample, can you show it again, sir?
Yes, the sample was 300.
Yeah.
Now, I know that the P was 0.1%, but you got to remember that that as a decimal is this fella. So NP, N times P, in this case is only 0.3, but N times P must be bigger than 10 or the sample's not good enough.
Oh, okay.
Now, another story, suppose N was 500 and P was 1.5%. You might think that that sample is big enough to use the central limit theorem process on it. But actually, if you go NP, you're going to go 500 times 0.015, which
So
I get,
7.5.
and it ain't bigger than 10. So that means you cannot use the central limit theorem, so the question is finished.
Okay. Thank you.
Right. I believe only the last two questions that happens, but I didn't do every single homework question. So you know that bit at the beginning where they get you to check everything? Almost all the time it's yes, yes, yes. But just, I'm not saying there is because I'm not sure, but just in case, will you make sure that you don't just say yes, 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 in case there's a no in there? Right? If the sample size is actually too small, you should just say no and the question's kind of over with. And that's fine. It means you've less work to do. Are we good?
Yes, sir.
Right. Now, unfortunately, time has